Hi student, welcome to this new video, still on diagonalization, but here we focus on solving differential equation. Another way of solving the problem of coupled first order linear ordinary differential equation is with the perspective of matrix diagonalization. Supposing that you have a system of equation x prime equals to ax, and this is the derivative with respect to time, and you are asked to solve this equation. Let's call this equation 1. Now, supposing that A is diagonalizable, that means that there exists a P minus 1AP which equals to D, and D is a diagonal eigenvalue matrix, and P holds the eigenvectors of A. Now, having said that, if we use a change of variable by saying that x equals to p y, right? And then we insert it in equation 1, we call this equation 2, and inserting equation 2 into 1, what do we have? We have that p y dot, right, equals to a p y, right? The next thing that we can do, if you observe, if we multiply both sides by the inverse of p, we have that p minus 1 p y dot equals to p minus 1 a p y. This leads to, right, y dot equals to dy. Now you should keep this is equation 3. Now, what do we realize here? We realize that the couple equation now has been transformed to an uncoupled equation that can directly be solved in the y variable, and then we can recover the solution in the x variable by using equation 2. Now, in summary, how then will we be able to solve such ODE? Summary. So the first thing that you have to do is to have the changing the variable, change the equation from x dot equals to ax to y equals to dy. Then secondly, what do you have to do? The second thing to do is to find the D matrix, which is also equal to finding the eigenvalue of A. And then 3, you find the P matrix, which is also to find the eigenvector of A corresponding to the eigen values of A. And then 4, once you have that, you can now directly solve equation 3, given here. And then the fifth step, once you have equation 3, you can now having y, you solve for y from equation 3, and then you can now finally solve for x in equation 2. That's a summary of the process, how you can solve the first order ODE using the principle of diagonalization. Let's have a look on this example. Example, solve this system of equation using diagonalization. The system is x1 dot equals to x1 plus x2, and x2 dot equals to 4x1 plus x2. Okay, how will you solve this? The first thing is trying to rewrite this as in a matrix form. So this can be rewritten as x1 dot x2 dot equals to 1 4 1 1 x1 x2. Okay, then we can see that this is resembling our equation 1, which is x dot equals to a x. Now, following the steps and the summary that we showed here, you have to transform, or you can easily do that by following the same process. transform this, right, to y dot equals to dy. So equation 3. Now, it means that you have to find matrix D, which is the diagonal eigenvalue matrix. So we have to find the eigenvalues. So you have to solve this equation, a minus lambda I equals to 0, leading to 1 minus lambda for 1 minus lambda. So if when you solve this, you will realize that you have that 1 minus lambda, okay, square minus 2 square, right? This will give you lambda plus 1. If you do the you complete the square, you lambda minus 1 and times lambda minus 3. So we can see that we have two eigenvalue. Lambda 1 equals to 3 and lambda 2 equals to minus 1. Therefore, we can write our D matrix over here, 3, 0, 0, minus 1. Right? Okay. So now we can find the P matrix, which is also indirectly finding the eigenvectors. So let's find the eigenvectors for lambda 1 equals to 3. Solving this equation, a minus lambda I v1 equals to 0 leads me to lambda is equal to 3. I will have minus 2. I will have 4. I will have 1. I will have minus 2. Right? Right in a Gauss echelon way. This will give me, so what can we do here? We can reduce, right? We can apply the Gauss reduction here. If we say that R2, the second row, equal to the second row plus twice the first row, we have 0 here, and we can divide the first row by minus 2. So I have 1, have 0, 0, 0, 0. Right? We can see that the first variable x1 is fixed, and the second variable x2 is free. So I can set therefore that that x2, right, equals to t. Then from the first row, I have that x1 equals to half t. Okay, therefore I can have my vector v1, which is x1, x2, which is equals to half t, which is t half 1, right, with t be any scalar. If I've now looking for the second eigenvalue, the second eigenvector for lambda equals to minus 1, solving the same equation, a minus lambda I v2 equals to 0, I have that I will have 1 minus 1, so I have 2, I have 4, I have 1, and I have 2. Okay, so having this, what can you see? You can see that if I do that R2, if I do that R2 equals to, if I do that R2 equals to R2 minus 2R1, this line will give me 0. And if I divide the first row by 2, it will give me 1 half 0, 0, 0. And x1 variable is fixed and x2 is free. And in the same way as the first one, I will have that v2 will be equals to s minus half 1, right, with s any scalar. So here we have, then I can then write my P. So we have our D matrix, right, 3, 0, 0, minus 1. Then I can write my P matrix. My P matrix is the matrix of the eigenvectors of matrix A. So this will give me, I can multiply this by 2, right? So I have 1 over 2, 1, 2. Multiply here, I'll have minus 1, 2. Now, I have P and D, so I can directly solve for Y. So the fourth step here, I can solve for Y, right? So I will have that Y equals to D 3, 0, 0, minus 1 times Y, Y1, Y2. This can be written as 3Y1 and Y2 dot equals to minus Y2. Right? So solving this is easy. I have that Y1 of t equals to exponential 3t, this is a constant, and Y2 of t equals to b minus t. So I have Y1 and Y2, then I can directly solve for x. Therefore, x will be given as, if I put it just here, so from 2 I have x, so x therefore will be x1, x2, which equals to p. P is 1, 2, minus 1, 2, times y, a, 3t, and b, minus t, right? And then you can leave it at this fine, or you can write it as a system of So I have that is a exponential 3t minus b exponential minus t, and x2 equals to 2a 3t plus 2b e minus t. So that is the final solution of this system of equation. We hope that you will be able henceforth to use the matrix diagonalization to solve system of differential equation. Thank you.